So hi, I'm going to do a very quick video today on waves. You guys have learned a lot of this stuff before, so I'm going to jump right in. Let me try and get a pointer going on here because that always helps things out. So you guys know this from before, but energy typically travels as a wave, we now know that waves and particles are kind of interchangeable, and you may be familiar with this. We call this the electromagnetic radiation spectrum, and it includes all the different types of, well, not all of them, but a number of the different types of energy that travel as a wave. They all travel exactly the same speed, super fast, 3.0 times 10 to the 8 meters per second, and we're particularly interested in this portion of the electromagnetic radiation spectrum, which we consider visible light, or we sometimes refer to affectionately as Roy G. Biv. If you notice here, as we go from the left to the right, the waves go from longer waves to shorter waves, and it also means our frequency goes opposite that. To that end, let's take a really quick look at a couple of formulas and a couple of waves. So if you take a look at these waves here, the actual wavelength is the distance from the crest to a crest, or really any point where a wave repeats itself. Now if you take a look at this, clearly these wavelengths are longer than these wavelengths, which are longer than these wavelengths. Now since all of these waves are traveling at exactly the same speed, the speed of light, it means that in this bottom wave, since the waves are a lot shorter, there's going to be more waves that pass a point per second, which means that the frequency is higher. And the equation that relates these two together is C equals wavelength times frequency. This lambda means wavelength, this nu means frequency. Why didn't they use W and F? Well, because they were taken up with work and force. So we have become pretty pro at working through these, but you should be aware that this right here, this is a constant, and it is 3.00 times 10 to the 8th meters per second. And this unit right here is in meters, and this unit here is in hertz. Now if you take a look at this, this is problematic because how in the world does a hertz cancel with a meter and a second? So let me just put the units in below here. So let's look at the units for C. If you look at the units for C, would you agree with me that it is meters per second, right? And then if I took the units for wavelength, they are meters. And if we were just to do a little bit of math and we're like, what's the only unit that could go right in here and would allow us to have seconds on the bottom? Ding, 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 you guessed it, we have per second. And so what you should be aware of here is the unit hertz really is the per second, or second to the -1. You should also be aware that although they'll always talk about wave or frequencies in terms of hertz, we will never ever write hertz into a problem. We'll always use this or this. True story? The other thing we can be aware of is this. Since this is a constant right here, typically what we're doing is, I don't know what just happened there, but typically what we can do is we can, given one of these variables, we can solve the other, and we can rearrange or isolate either of these two. Now, I'm going to jump forward here a little bit, and I'm going to introduce you to another formula. And this is actually a really important formula because it relates energy to frequency. So here's frequency, here's energy, and this right here is a constant. I've written it down below because I did not want to write this whole thing out, and of course I just put a line through it. But Planck's constant, or H, is 6.626 times 10 to the -34th joules times seconds. Now the other thing you need to be aware of, and you may see this in a slightly different form, but this H times nu, we refer to that often as a quantum. In fact, that is how units of energy are measured. H times nu. You will see a different formula that looks a little something like this. It goes change in E equals N H nu. And what that means is this N is the number of quantums we have, and this H times nu is a quantum. Now you should notice something here. A quantum is constant times frequency. Pretty sure constant doesn't change because, constant. But frequency can change, which means that the energy in a quantum goes up when our frequency goes up. So this formula right here, E equals H nu, is one that we use quite often. If you rearrange the C equals wavelength times frequency formula to isolate nu, you'll get C over lambda. And if you take this C over lambda and plug it into this equation right here, this is how you get this right here. That's a useful equation. But the big takeaway from this is that energy, and you've noticed how they wrote energy of a photon. Photon is just a light energy quantum, is equal to quantums, or however many quantums n that you're passing along. So if I want to pass one quantum to you, that's the least amount of energy I could ever give you. If I want to pass a lot of energy to you, I'm going to have to pass a lot of quantums. Now, we're going to talk about that a little bit more in class, but you should be aware of this equation. And where did that lead us? It led us to the idea that energy comes in only specific units or specific increments, which, when Bohr got a hold of that, he said this, what if I make a nucleus, and what if I say, that's my nucleus, I made a little positive sign there because, you know, nucleuses are positive, and what if I then treated electrons as moving solely in orbits surrounding the nucleus? I'm going to switch over here to my my laser pointer. And so he said, what if I have an electron right here and it's circling around, but then energy hits it and it bumps up to another energy level? Well, once it's there, it's not going to be happy and it's going to want to fall back down, but it has multiple drop downs it could have. Could it drop from the 5 to the 4, or the 5 to the 3, or the 5 to the 2? And I wish that I had realized that this was actually one of the energy levels here. So I'm going to pretend that this is just a little circle in the center where the nucleus is. He actually came up with the idea that there are 7 energy levels in an atom, 7 orbits, and we're like, that sounds awfully familiar. That's because we borrowed from him and we said, well, there's going to be 7 energy levels in an atom altogether. Not orbits, but energy levels. Now, what you need to be aware of is all the math that he did worked perfectly for hydrogen, because hydrogen only has 1 electron. It's kind of nice when you scheme in advance to only have 1 electron. It means that no other electrons are messing with you, and it actually worked. And so he thought that he was onto something really, really big. We'll talk about some of the formulas in class. But I want you to notice something here. Do you see how it shows here that an electron, if let's say it was way out here, so let's say the electron's right here, and it were to fall down, see the ziggity-zaggity line, all the way down here, that fall down from here to here would have to release energy, because the only way you're going to drop energy levels, and let me remind you again, this first energy level, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, the farther you go from the nucleus, the more energy your energy level has. N means your energy level, or main energy level. So if we take a look at this, electrons want to live in the lowest energy levels possible. We call that the ground state. But when energy hits into them, they jump up to higher energy levels. They aren't happy and they fall back down. Now, a lot of the fallbacks we never see, because when energy is given off, only a few forms of energy, let me jump back down here to you, only a very few forms of energy, the visible spectrum, do we see. A lot of forms of energy, all of this right here, we can't see. So let's jump back here to this equation, or this particular formula. And so if you notice here, you see how there's a particular color light here, and I think it's blue light, only occurs when you jump from the 5th down to the 2nd. And when you do the, I don't know what that is, but if you jump from the 4th to the 2nd, or the 3rd to the 2nd, you have different color light being given off. Incidentally, it's really important that if you jump from the 4th to the 3rd, or the 3rd to the 2nd, the 3rd to the 2nd isn't the same energy fall down as the 4th to the 3rd. Super fun fact. Let me put it into a little more complicated graph, because again, graphs are our friend. If you take a look here, this is the energy, and these are the energy levels. So if you take a look here, the first energy level, then we have the 2nd, 3rd, 4th, and 5th energy levels. Now, if I'm an electron and I jump up to, let's say, the 5th energy level, I have the option of jumping from the 5th to the 4th, the 5th to the 3rd, the 5th to the 2nd, or the 5th to the 1st. Now, the 5th to the 4th gives me no energy level, or no wave that I can see, but it still gives off energy. But if I were to drop from the 5th to the 2nd, it's going to give off a wavelength of light that is blue that we can see. Similar, if I drop from the 4th to the 2nd, it gives off green light. If I drop from the 3rd to the 2nd, it gives off red light. If I drop from the 2nd to the, you notice here there is not a, I don't know why that happened. If I drop from the 2nd to the, that was a neat trick. If I drop from the 2nd to the 1st, notice how there's no color in here? That's not because energy doesn't give off. There is indeed a lot of energy that's being given off, but that energy corresponds to a wave that we can't see. The biggest takeaway from this, from what Bohr did, is simply this. Because there's only certain lights that are shown when electrons drop down, it must mean there's only certain energy levels in an atom. And that was really, really huge, because it meant that energy is quantized. So this idea that energy is quantized means that energy can only occur, well, that's a neat thing, can only occur in specific increments. And that's one of the things we're going to camp on. And in fact, we're going to go in class tomorrow. We're actually going to jump into the idea of how does that play with orbitals and energy levels. So this was a very short but sweet video. Hopefully it makes a little bit of sense, and we'll talk a little bit tomorrow. See you then.